Okay, welcome to lecture. We'll get started in a minute or two, picking up from where we left off, which was talking about types of reactions, which I believe is chapter 5. So I believe we're right around here. And again, we'll get started in just a minute or so. As usual, if you do have questions, feel free to ask them in the chat box there, and I'll get to your questions, even if I maybe have moved on from that slide. I'll make sure to get to it. So again, we were talking about types of reactions. I believe we're sort of towards the end here of double displacement reactions. And again, we will pick up here in just a second. All right, so let us get started then. So we basically been talking about types of reactions, ways to classify reactions, and we've been talking about sort of a big classification of reactions, which are our double displacement reactions. And remember, in a double displacement reaction, the way you recognize it is you're starting with really two ionic compounds. So something is positive and negative. And ultimately, what happens in a double displacement reaction is the two positive ions, the two cations, will switch partners, and they will make two new ionic compounds when they do switch partners. Now, sometimes this sort of switch results in a solid being formed on the product side. And that's sort of a special type of double displacement reaction, which is, as we were talking about, a precipitation reaction, which is another way to classify a certain type of double displacement reaction. Again, a precipitation reaction essentially means that some type of solid has formed from the mixture, say, of two solutions. And it is a double displacement reaction. Again, can also be classified as a precipitation reaction because it did make that solid. These are the reactions where we also saw the different types of equations that you could write. That is our molecular equation, our total ionic equation, and our net ionic equation. And remember that these guys are the equations that really sort of describe what's happening in the solution when you mix a couple of guys together. The total ionic equation, we break apart everything that is aqueous. That's a strong electrolyte. We keep together things that are solid, liquid, or gases, or again, if they happen to be a weak electrolyte, they wouldn't break apart. After you do your total ionic equation, again, you'll be able to find some ions on both sides of the arrow, which are our spectator ions. Those guys are there basically just to kind of balance out the charge. Once you cross out the spectator ions, what you're left with is the third reaction there, the net ionic equation. And that net ionic equation is really the equation that describes sort of what is happening in this reaction, what is truly coming together to form the product. So if it was a solid product, It would be the two ions that would come together based on solubility rules that would form that solid. So we're going to move on here then to another type of really a double displacement reaction. These are also sometimes referred to as acid-base neutralization reactions. And an acid is basically something that can produce H plus ions in solution. H plus ions are sometimes referred to as a proton. H plus and H3O plus, when we talk about acid and bases, are essentially the same thing. They basically mean the same thing. They mean really the acidic part of the solution. So something that has that ability to produce H plus in solution, free H plus, is considered an acid. Bases, on the other hand, are substances that when they do go for a swim or in a solution, they're able to produce hydroxide ions. And over here is our hydroxide. Now, a lot of strong bases, things like sodium hydroxide, potassium hydroxide, they actually do have hydroxide in the actual formula. And a lot of guys in group 1 and 2 on the periodic table are where a lot of our strong bases come from. But not all bases necessarily has to actually have hydroxide in it. A good example is what they have up here, which is ammonia, NH3. NH3, although it does not have OH minus in it, when it reacts with water, it is able to basically take the H plus from water. And when it takes the H plus for water, it becomes NH4 plus, which is the ammonium ion. And by that little process right there, it is able to produce hydroxide in solution. So although it doesn't have hydroxide, and different than something like sodium hydroxide, which essentially all it needs to do is go for a swim and is going to break apart into Na plus and OH minus. And that's why sodium hydroxide is considered a strong base, because it essentially just needs to go into the solution before it breaks apart. While NH3 is a weak base because it needs to go find some water, do a little bit of a reaction to generate the hydroxide. So since they both are able to generate that OH minus, they're both considered a base, one being a stronger base than the other. Again, because it doesn't need to go find anybody to produce hydroxide. It sort of has hydroxide built into it already, like sodium hydroxide and potassium hydroxide. Now, typically, whenever we take an acid and base, and especially when we take a strong acid plus a strong base, we get the two things that we see at the very bottom of the screen. We get what is referred to as a salt and water. And really, the water part comes from the H plus from the acid, coming together really with the OH minus from the base. And these two guys, when they come together, is essentially how we do get the water. A salt, which is the two things that you commonly get here, salt and water, when you mix an acid and base together. The salt is really just a fancy word. I don't know how fancy it is, but it's really just an ionic compound. So basically, you're a positive and negative guy together. So we say that basically when we mix an acid and a base together, we typically will form water and a salt. Again, H plus from the acid, OH minus from the base is typically where our water comes from. And again, our salt is really this, honestly, these sort of spectator ions that are there is typically where our salt comes from. So another type of double displacement reaction is an acid-base reaction or an acid-base neutralization reaction. And really, we can kind of see how this reaction looks, but just for your own purposes here, these are some strong acids and some weaker acids. So up here, these are really the kind of 1, 2, 3, 4 acids, along with HBr is a strong acid. That's hydrobromic acid. HI is also a strong acid. That's hydroiodic acid. So, these sort of 6 acids are essentially strong acids. Then we have some weak acids like acetic acid, hydrofluoric acid, carbonic acid. These are weak acids. So remember that strong acids and even strong bases, acids are bases. They are both strong electrolytes. And if you remember, strong electrolytes are guys that when they go into water, 100% break apart into ions. So they 100% break apart into ions. While if we have some weak acids like we do down in this region here, weak acids and also weak bases, they are weak electrolytes. Weak acids are bases. There are weak electrolytes. And if you remember, a weak electrolyte is something that will mainly stay together. So it will stay together like HF in the solution. And it will produce a little bit of the ions. So it's still able to break apart. So we get a little of the ions, for example, that will form, but it will mainly stay together. So when we do have something that's a weak electrolyte, a weak acid, or a weak base, if you happen to come across it in a net ionic equation, or for example, a total ionic equation, anything that's a weak electrolyte will stay together. So if you had HF, you wouldn't break it apart because it would mainly stay together and it would stay on the reactant side kind of complete as HF. Here is some common bases, same idea. Again, you can see a lot of group 1 and group 2, and especially those guys that have hydroxide in them. A lot of those guys that actually do have hydroxide in them are essentially weak bases. I'm sorry, strong bases, while guys that don't necessarily have hydroxide in them are more on your weak side. By the way, this is ammonia, and it is a weak base, as we've been talking about there, but very common. Sometimes people will call it ammonium hydroxide. That's essentially what it is when it's in a solution form. It's basically ammonium hydroxide. So sometimes, especially if you take 1B, you'll see ammonium hydroxide written a lot in place of ammonia. Again, it's basically the same thing. So these guys are called acid-base neutralization reactions because the ultimate sort of net ionic equation that's happening here, again, you could look at this just like a traditional double displacement reaction. Our acid is really H plus and Cl minus, Na plus and OH minus. Again, a positive negative guy and a positive negative guy. And again, these two guys are going to switch partners in this case. That means the H plus and the OH minus will come together to make our water. And again, our salt is from the leftover part, which is the sodium and the chloride. If we write the total ionic equation for this guy, we would break apart our strong acid into H plus and Cl minus. We would also break apart our strong base into Na plus and OH minus. And on the other side, our sodium chloride, which is a strong electrolyte, will also break apart. And our water, which again is a pure liquid, which is not written here. All these guys are aqueous, by the way. AQ. And again, this represents, as we talked about last time, our total ionic equation, our complete ionic equation. And the name implies that these should have ions with charges. Again, if we look and see on the left-hand side and the right-hand side, we will see ions that look exactly the same. And those are our spectator ions. They are really not there to form any of the product. They're just there really to balance out the charge and watching. In this case, it is the sodium and the chloride, which are our spectator ions. And as I mentioned before, they are typically what makes up our salt, by the way, which is this guy. And when we cross it out, we are left with our total ionic equation, our net ionic equation, net ionic equation. And this is truly what is happening in this reaction. It is the H plus from the acid that's getting together with the OH minus from the base, basically to form our water. This is also why it's called an acid-base neutralization reaction, because essentially what you made is water, basically H2O. And again, this is overall a double displacement reaction. It is probably most often classified as an acid-base neutralization reaction. And again, the net ionic equation, to be honest with you, no matter what combination of a strong acid and a strong base that you put together, when you work it all the way down to the net ionic equation, if you mix a strong acid and strong base, you will always get the exact same net ionic equation. It will always be the formation of water. Any questions on that there? And again, a reminder, if you do have questions, feel free to type them. Even if I maybe have moved on, we'll go back and make sure we answer them. Okay, so continuing on in ways to classify reactions. Again, here's kind of visually what's going on. We have our H0 plus or Cl minus or sodium ions or hydroxide ions. Again, going to make our salt and water when we mix them together. Now, some double displacement reactions will actually produce gas. So there are some, oops, come back, there we go. There are some reactions that will produce gas as a product. And there's sometimes two ways in a sort of a double displacement reaction that a gas can be generated. Up here on top is really a direct generation of those gases. This again is a positive, negative guy. Positive and negative guy, again, are two positive guys going to switch places, where the potassium will end up with the sulfate to give us potassium sulfate. And the H plus here and the sulfur, which is -2, and H plus, which is +1, will give us hydrogen sulfide gas, a deadly, toxic, very smelly gas, especially if you've ever smelled anything that involves sulfur. Does not smell very pleasant. So this one, directly as a result of that double displacement reaction that occurs, or that double exchange that occurs, directly will produce a gas. So this is, again, still a double displacement reaction. Unlike the couple other ones that we saw, we did not generate a solid. We did not generate a liquid like water, but here we actually were able to generate a gas in this case. Again, if we look on the bottom here, this is also a double displacement reaction. This is our positive guy. This is our negative guy, our positive and negative. Same deal going to happen here. We're going to get a switch that occurs that gives us our potassium sulfate and our H2SO3. This H2SO3 is sulfurous acid. And sulfurous acid will actually then go through another type of reaction, which is known as a decomposition reaction, which we'll see in just a sec. And a decomposition reaction is essentially where you take something and you break it apart. So you take like one thing and you break it apart into a couple other things. And in this case, it will very quickly, as you can kind of see over here, kind of very quickly decompose into water and sulfur dioxide gas being generated in this case. This is an indirect method of generating the gas. It is a double displacement reaction. Followed by an immediate decomposition reaction to generate that gas. So it's almost like a two-step process that occurs relatively quickly. We might have seen this before, not this particular gas, but I believe we might have done it if you take an acid and some like sodium bicarb, for example, also a double displacement reaction happening. We will get sodium chloride plus a little H2CO3. I'm not going to balance it at this point, but maybe a 2 there, and probably a 2 there. And what usually will happen here is this is almost identical to what's made here. This is carbonic acid, and carbonic acid will very quickly go through a decomposition reaction, and that will generate our CO2 plus some water. Here we're generating carbon dioxide gas, And that's usually some bubbles and stuff that you see when you would do a reaction like that. Kind of like the old Alka-Seltzer commercial, plop, plop, fizz, fizz. Yeah, that fizzing and stuff, again, is that sort of CO2 that's being generated as something like, you know, the antacid sort of reacts with the acid, is generating that carbon dioxide. Any questions on that? And that's what we see here, kind of all that fizzing is that CO2 that's being produced, again, from that decomposition reaction that occurs, you know, relatively quickly. This table just sort of summarizes some different gas-producing reactions, and some of them are direct, some of them are indirect. So here again, the one that we saw, if we take a metal that has sulfur in it, and we react it with an acid, this is typically the gas that we generate directly. If we take a metal that has carbonate in it, carbonate will typically produce our carbonic acid, and usually will then go through a decomposition reaction to produce the CO2 like we saw. If we have a metal that's connected to sulfite, ITE, it will produce sulfurous acid, again, very similar to this guy. It will go through a decomposition reaction, and that's where we will generate our SO2 gas. And anything with ammonium in it, if I don't hit that, I come back. Anything with ammonium in it that reacts with a base will produce ammonium hydroxide, and that will be in equilibrium through sort of a secondary decomposition reaction to produce ammonia. So this is just sort of a summary table that kind of helps you decide, you know, in this double displacement reaction, although a lot of times what you get on the product side is a solid and perhaps water or a liquid, you can, again, in certain situations through a double displacement reaction, actually generate neither of those, but generate a gas instead. By the way, obviously, if we had a gas and you had to do some type of total ionic equation, net ionic equation, those guys would also stay together, as the gas would not form into any ions or anything like that. It would stay together if you came across those in maybe a study assignment or something like that. Okay. So that pretty much wraps up sort of the big umbrella of double displacement reactions. So now we're going to talk about really another important sort of big category of reactions, and these are oxidation reduction reactions. These are also what are sometimes referred to as redox reactions. And redox reactions means oxidation and reduction. Oxidation means that you have lost electrons. Reduction means that you have gained electrons. Those are two definitions of them. So sometimes people remember this by Leo the lion goes grr. Loss of electrons, oxidation. Gaining of electrons, reduction. Sometimes people remember it by the classic oil rig. Oxidizing is losing. Reducing is gaining. If you don't want to choose, you could put them together, put Leo the lion on the oil rig, and then he will go grr, and you don't have to choose. You can just remember them both. When we talk about losing electrons and gaining electrons, that obviously has an effect on what is really known as the oxidation number or oxidation state. Sometimes people think of it almost like a charge. And a very sort of simple way that you could sort of figure out what is happening with a particular sort of substance, is it being oxidized or is it being reduced, is you could just use really a basic number line. And if you use sort of a basic number line, somewhere there's zero. And to the right of zero is usually the positive numbers, right? To the left of zeros are negative numbers. And when we think about what's happening is if I lose electrons, we should know this, right? If you lose electrons, that means that you are going to become more positively charged, right? Because you have now more protons than electrons. So you become more positively charged. So if you look at the number line and you're moving in this direction towards the positive side, that usually will mean that you are going through oxidation. The opposite is true when we go through reduction, and when we gain electrons, that means that we are going to become more negative. So when we gain those electrons, we become more negative, and that means if you're on the number line here, you're moving in this direction and you're going through reduction. So you could almost just kind of put where you are on the number line, and are you moving to the left, are you moving to the right, and that will help you determine, if you are going through oxidation or reduction. So for example, if we look at these two reactions down here, this reaction right here is magnesium. And when we do this reaction, essentially the overall reaction is what we got on the bottom there. It's right here. If we look at this overall reaction, magnesium on the left-hand side has a 0 oxidation state. Remember that anything that is by itself, uncombined, does not have a charge. Things only get charges, metals and nonmetals only get charges when they combine together. So things in their natural state, metals and nonmetals that are not combined with anything else, will have an oxidation state of 0 and really have no charge, if you want to think about it that way. That also means that when we look at our oxygen here, it also does not have a charge. That is naturally how we get oxygen. It is only when we come to this side where the magnesium and the oxygen have come together to make magnesium oxide, that is when we get our charges. And our magnesium here is +2, group number 2 on the periodic table, and our oxygen is -2 in this case. And we can use this sort of number line to help us decide what is being oxidized and what is being reduced if we're not sure. So for example, if we look at our magnesium, going to our magnesium over here, our magnesium started at 0, and then it ended at +2, which would be heading in this direction, which means in this case, the magnesium is, like it says here, going through oxidation, is becoming more positive. Now, if we look at the oxygen, we can figure the same thing out for the oxygen by looking at our oxygen over here, which is starting at 0, and then our oxygen will end at -2. So same deal, you could go to your number line. Oxygen is starting at 0, and -2 is heading in this direction, which means that we are going through reduction like we see here. And again, by just using that basic sort of number line, and if you can figure out really the oxidation states, which we'll talk about in just a second as well, how to actually do that, are the charges, if you kind of want to think about it that way, you could basically figure out what is going through oxidation and what is going through reduction. The other nice thing about oxidation and reduction is they always occur together, which means that if you can identify one thing that went through oxidation, by default, the other guy had to go through reduction, and vice versa. So if you could figure out what was reduced, you could figure out what is being oxidized. Now, one way that we sometimes can write sort of what is going on is by writing these things as what is known as half reactions. They're called half reactions because essentially if you add them together, you will get the overall reaction that's taking place. So our top one here with magnesium is our oxidation half reaction. Again, our magnesium is going from 0 to +2, which means it is going through oxidation. It is losing electrons. And the way that is represented is the electrons will be on the product side. So if you see electrons on the product side, that is an oxidation half reaction. It's like those electrons are being given off or being lost. So that's why the electrons end up on the product side. Now, the opposite is true when we go through reduction. When we go through reduction, things are gaining electrons. Again, if we look at our oxygen here, it went from 0 to -2. becoming more negative. And what we see is the electrons are actually on the reactant side. And whenever you have electrons on the reactant side, that is representative of a reduction half reaction. Like those electrons are being gained, like that O2 is being gained, gains those 4 electrons to get to our oxygen with a -2 charge. So when you write half reactions, if it's the oxidation half reaction, you should have the electrons on the product side. If you are writing the reduction half reaction, the electrons should be on the reactant side. The other thing that you'll also notice is if you do it correctly and balance it correctly, you should have the same number of electrons in both half reactions. Because in order for something to lose electrons, something has to gain those electrons. So the total number of electrons that is gained or lost is the same number. And that's why we have 4 electrons in each. Why do we have 4 electrons in each? Because technically speaking, O2 is 2 oxygens, where each oxygen will gain in the balance equation 2 electrons. And that is also why we needed 2 magnesiums, because each magnesium here will lose 2 electrons. Grand total of electrons lost, 2 and 2 is 4. Grand total of electrons gained, 2 and 2 is 4 in this case. So all that sort of balancing, and you should always make sure it's balanced, comes about with sort of balancing the equation. And that's why, again, you may go, well, I thought magnesium lost 2 electrons. Why is there 4? Again, it is 2 electrons, but it is 2 electrons for each magnesium, just like each oxygen will gain 2 electrons to give us a total of 4. Any questions on that? Okay. And a lot of redox reactions, which again is sort of a big classification of reactions, a lot of what's happening is typically when we get the guys that are, for example, have a charge, typically these guys that have charges are the ones that are aqueous. They're basically the ones floating around in the solution. We'll just draw some dots on there. Now, when these guys sort of lose charges, like we see here, they basically get plated on like a metal, for example. They go from swimming in the liquid part to basically becoming something with no charge. So it becomes almost like a solid, especially if it's a metal. And that's why when we look at the pieces of metal here, we see kind of almost plating of the metal on there. And that's basically all those ions that are essentially coming out of solution, losing their charge, and they essentially get plated onto the metal. And the same idea as what we see on the right-hand side as well. Here's another sort of reaction here. And this reaction is also a redox reaction if we look at it. If we look at sort of the oxidation state of zinc, again, all by itself, not combined with anything, has a 0 in terms of its oxidation state. The zinc over here, though, when it combines with the sulfate, has a +2 oxidation state. The copper over here has a +2 oxidation state. The copper over here by itself solid has a 0 oxidation state. And for the time being, we'll keep these together. We don't have to, and we won't shortly, but we'll keep them right now together. Sulfate on this side is -2. Sulfate on this side is -2. In terms of what's happening with sulfate, nothing's really happening with sulfate. Nothing's really changing with those sulfur or the oxygens. So again, if you want to kind of look and see, we make that kind of number line, positive and negative here. If we look at our zinc, it is going from 0 to +2. So our zinc, which is starting at 0 and heading +2, which would be in this direction. And again, when you move in that direction, that means that the zinc is going through oxidation. While if we look at our copper and see what's happening with our copper, which truthfully we don't really need to see because we've already figured out one, but just to show you, copper is actually starting at like +2, which we'll call over here, and it's ending up at 0, which is moving in this direction, which means when you move in that direction, it is going through reduction. So this is really a redox reaction that's happening, and we can basically write what is truly happening here. The zinc is then going to zinc with a +2 charge. And again here, as we saw earlier, the zinc is going through oxidation. It will lose 2 electrons. And this would be our oxidation half reaction. While our copper is starting at +2, it's going to gain those 2 electrons and end up at copper with no charge in this case. And this is what is known as our reduction half reaction. Now, again, they're called half reactions because if you want the overall net ionic equation that's happening, you could add both of these reactions together. Before you could ever add a reaction together between an oxidation and reduction reaction, you always want to make sure that the electrons are exactly the same in both half reactions. If they are not, then you do need to multiply. So for example, let's just hypothetically say the top guy had 3 electrons and the bottom guy had 2 electrons. Common number would be 6, so you would need to multiply the top one by 2. You would need to multiply the bottom equation, the entire equation, by 3. So when you take an oxidation half reaction and a reduction half reaction and you want to add them together, this is always accomplished by you got to first make sure that you have the same number of electrons. Again, the idea here is if somebody loses a certain amount of electrons, somebody will gain the same amount of electrons. And I'll cross it out lightly here. I'll just dot it. Because they are on opposite sides of the arrows and they are exactly the same, those electrons will cancel each other out. And this will give you the overall really net ionic equation that is happening. The zinc with no charge plus the copper with 2 plus charge is going to form our zinc with a +2 charge and our copper with no charge on this case. This is what is sometimes referred to as a net ionic equation of what is happening for this redox reaction. And believe it or not, you could get the net ionic equation doing the exact same things what we did with our double displacement reaction. If we take our original equation up there, we would keep our zinc together because it's a solid. We would break apart the copper 2 sulfate into its ions. Because it's aqueous, the zinc sulfate will also break apart. And the copper would stay together. Since it's a solid, we will see that basically the sulfate is our spectator ion. And if what you're left with is this guy right here, right? So this would be almost like your total ionic equation that you did with our double displacement reactions. Any question on that? This reaction here, although it is a redox reaction, as we will see in just a second, can also be classified as a single replacement reaction. And in a single replacement reaction, which is again another way that you can classify this particular type of reaction, you essentially will have one thing that's either a metal or a non-metal. plus an ionic compound, something that's positive and negative. And basically, for example, if it's a metal, it will come in and replace that B, and that will give you A and C, plus this guy will come off by itself. So basically what's happening in this reaction, the zinc is coming in, it's kicking out the copper. When the copper gets kicked out, it just becomes copper by itself. And when the zinc comes in, that's when it gains its charge. Now, if this was a non-metal, let's cross it out there. This was a non-metal A, same reaction would take place, except that it would come in and kick out the negative guy. Again, the metal comes in and kicks out the positive guy because although the metal does not have a charge at that moment, when it gains a charge, it's going to be positive. When a non-metal comes in, although it does not have a charge, when it comes in, it will get a charge of negative, so it will kick out that guy. And that will give you B and A plus RC. Perhaps you remember that experiment we did way back when we were doing the halogens in the fume hood. Those were all these type of reactions. These are all redox reactions. When the halogen went from the top layer to the bottom layer, from the bottom layer to the top layer, those again were all single replacements. And perhaps you remember that in order for this reaction to take place, whatever is coming in needs to be more reactive than what it is replacing. And again, if it's less reactive than what it's replacing, the reaction will not take place. So the guy coming in has to be more reactive. Any questions on any of that stuff there? Before we move on from this slide here and we're going to continue to talk about redox, but before we do, another aspect of redox is, although we know that there are things that are being oxidized and there are things that are being reduced, there is actually ways to classify things as either the oxidizing agent or the reducing agent. Now, the oxidizing reagent or the reducing agent, these are not the things being oxidized or reduced. They are the oxidizing agent or reducing agent. The oxidizing agent is actually the thing that gets reduced. So the thing that is going through reduction on the reactant side is the oxidizing agent, while the reducing agent is the thing that is getting oxidized. So you want to be careful if they ask you about the oxidizing agent or reducing agent. They are not talking about what is being oxidized or what is being reduced, but it is actually the opposite of the name. The reason the name is opposite is the oxidizing agent is the thing that gets reduced, because in order for something to get reduced, it has to gain electrons. In order for something to gain electrons, something has to get oxidized. And that is what is causing the oxidation in the other reactant. And vice versa for our reducing agent. In order for our reducing agent to get oxidized, it needs to gain electrons. I'm sorry, it needs to, let's say that right again. In order for something to get oxidized, it needs to lose electrons. When it loses electrons, it will cause the reduction in the other thing. So the oxidizing agent and the reducing agent, the easy way to remember it is opposite of its name. So essentially it would be opposite of its name in terms of what is happening. So if we look at the reaction that we have on this page that we just did, what we see is the zinc here is going through oxidation, which means by default, our zinc would be our reducing agent. Again, because zinc is able to lose those electrons, it will cause the reduction of, in this case, copper. So because it lost electrons, it causes the reduction in something else, and that is why it's known as the reducing agent. While in this case, the copper 2 over here, which is going through reduction, will be our oxidizing agent. For the exact same reason, because the copper is going to gain electrons, it will cause something to lose electrons and go through oxidation. When you're asked to identify the oxidizing agent and reducing agent, they are always found on the reactant side, not the product side, but always the reactant side. So that is always where you should find them. So if we go back to our magnesium and our oxygen here, again, in this case, the magnesium is going through oxidation. So the magnesium here with no charge would be our reducing agent. And our oxygen here, which is going through reduction, would be our oxidizing agent in this case. All right, so again, what is being oxidized and reduced is different than what is the oxidizing agent and reducing agent. And pretty much what's behind there is everything I scribbled on the board, I think, here. Except there was an example here. And that example is very hard to see, I think, in this case. So, copper and silver nitrate. So I'll do that one up here so we can see it. So the one that's kind of got scribbled out on the bottom there, we have copper and silver nitrate going to copper 2 nitrate and some silver and a little bit of a 2 there, perhaps a 2 there, and I think that looks right. Right. Oops. Copper and silver. Perfect. And when we look at this and get in terms of being oxidized and reduced, our copper is 0 here. Our copper is plus 2 over here. Our silver in the silver nitrate is plus 1. Our silver over here in the solid state is 0. So again, if you look at your number line, for our copper, we're starting at 0. And we're going to plus 2, which is going in this direction. So our copper is going through oxidation, while our silver, which is starting at plus 1, which would be over here, and ending at 0, which is moving in this direction, would go through reduction. And that means in this case, since the copper is going through oxidation, the copper would be our reducing agent. And the silver, in this case, which is going from plus 1 to 0, is going through reduction, would be our oxidizing agent in this case. And again, this is a redox reaction where, as it's showed on the other side there, the copper going to copper 2 plus 2 electrons, which is our oxidation, and our silver gaining 2 electrons, 1 each, going to our solid silver. So this would be our reduction half reaction. This guy here would be our oxidation half reaction. All right, so what will help us determine what is being oxidized and reduced is being able to correctly identify the oxidation numbers. It is also sometimes referred to as the oxidation state. And that is essentially the charge the atom would have in the molecule if pretty much all the electrons were completely transferred. So there are some rules here, and let's go over these rules just to see them. First off, kind of like what we did, and again, the oxidation number or state is not 100% always the same as the charge we think about certain elements, especially when we're doing sort of like nomenclature. So sometimes things that we normally think of as being negatively charged can, in certain cases, have a positive oxidation state. So it is slightly different than charge, but sometimes people think about it in that sort of sense. If you have anything that is uncombined by itself, like the metals that we saw, like H2, O2, way they naturally come uncombined, they will always have an oxidation state of 0. So that's why the copper up there that was by itself had an oxidation state of 0. The silver on the right-hand side that wasn't combined with anything has an oxidation state of 0 as well. Now, if you have a monoatomic ion, that means just one ion. It typically will have the same oxidation state as you would normally kind of think about it. So for example, if you had iron 3 chloride, the iron would have a +3 oxidation state. If you had iron 2 chloride, it would have a +2 oxidation state, the iron. Lithium, which is group 1, always going to be +1, will have a +1. When you go to the sign oxidation states, this guy right here is usually a pretty good place to start. And you usually will start with the oxygen. Oxygen will have a -2 oxidation state usually. The one exception where oxygen will not have a -2 oxidation state is number 3 here. It is actually in something where you have O22-. That is really peroxide, like hydrogen peroxide. And if you do have that, it actually has only an oxidation state of -1. It doesn't occur a lot, but it does occur occasionally. And hydrogen peroxide is a common one, sodium peroxide. The way you can almost recognize it a lot of times is, you got that extra 2 in there, where you might not have that extra 2 if it was oxygen with a -2 oxidation state. So not 100% of the time you have that extra 2 there, it's peroxide, but a lot of times it sort of is, and that's a good way to sort of recognize it. Continuing on with sort of the rules for oxidation numbers. The oxidation number of hydrogen is +1, except that when it is bound to a metal, it will come second, and then it will be -1. So for example, like if you had LiH, remember LiH, H here is hydride, which is the -1 version of it. So that's a sort of a rarity as well, but does occur. Again, needs to be hooked up with a metal for that to occur. Otherwise, hydrogen will be +1. Everybody in group 1 is still +1 in terms of their oxidation state. Everybody in group 2 is +2. Fluorine is -1. The sum of the oxidation numbers, when you add them up, needs to equal the overall charge if it's an ion, or if it's a molecule and has no charge, should equal 0. So when you add up all the oxidation numbers, it does need to equal the charge on it. And again, if there's no charge, they need to add up to 0. Oxidation numbers does not necessarily have to be a whole number. You can have something where an oxidation state is like -0.5, and superoxide is an example of that. This guy would have an oxidation number of -0.5. So let's just see how this works. So if we have HCO3-, which is bicarbonate, and a lot of times if you go about assigning oxidation numbers in a ion or a molecule where there is like kind of 3 sort of elements, usually a good place to start is with the oxygen. Oxygen would be -2. There's 3 oxygens. That would give us a grand total of -6 if we added them all together. Usually in a situation of 3, you go to the right where the oxygen is, you go all the way to the other side where the left is, and hydrogen would be +1. So in this case, if we add up what we got going so far, we have -5. Now remember that carbonate here does not equal 0, but has an overall charge of -1. So to get us to -1, in this case, the carbon does need to be plus 4. Any questions on how we got there? When you're asked to give the oxidation numbers, much like what it came across there, this is how you do it. +1. The carbon is +4. The oxygen is -2, not the grand total of what you got. When you're asked for the oxidation number, it wants just the oxidation number on one of the elements by itself. So the correct answer here should be -2, not -6 for the oxygen. The other important thing is you should include the charges. Yeah, so the charges need to be there. So that's why you need to write the plus, and in this case, the minus. Any questions on how to assign the oxidation number there? All right, so I think we have an example. Why don't you guys give it a go here? See what you come up with. This is just a chart of some different oxidation numbers. And again, you can see some things that we normally think about, like sulfur is -2, can be a lot. Even chlorine, as you can see, can have a lot of different oxidation numbers. Mn, for example, nitrogen, which we think as a -3 always, can have a variety of oxidation states. Again, the ones in red here are the more common ones, but it can potentially have positive ones when we think about things as being negatively sort of charged. So take a minute or two here, calculate the oxidation numbers of each of these guys that are present, and then we'll go through them. So take a moment or two to do that. Okay, so let's take a look and see how we're doing. So we'll start over here on the left. So again, in a situation where you got kind of three, usually go right, go left, and kind of save the guy in the middle there for the end. So here we have oxygen, which means that's going to be a -2. Again, it's not peroxide here. Again, with the three of them gives us sort of a grand total of -6. Going to the far right, because sodium is group 1, we will have a +1 for it. Now, in this case, when we put this together, we got our -5 like we had last time. But here we do not have any charge on the overall thing. It's 0. So we need to get to 0, which means the I in this case will be +5. And that means our sodium is +1 in terms of the oxidation state. Our iodide is +5. And our oxygen in this case is -2. So again, as I mentioned before, oxidation state slightly different than charge as we normally think about I in terms of -1. So again, slightly different when you do oxidation states are numbers. Coming up here to our fluorine, fluorine always going to be -1, which in this case means that's -7. The iodide in this case does need to balance it out to 0 as there's no charge. So here again, our iodine will end up as a +7 in this case in terms of its oxidation state. Again, you want to give the charge with it. And again, like here for our fluorine, although they all add up to -7, the actual correct answer for oxidation state is just -1. Now, lastly here, that's potassium dichromate. I think I took chemistry once. I think that's what it's called. And over here, this is oxygen. Again, going to start there with our -2. That gives us a -14 action going on. Over here at our potassium, our potassium is +1. Here we go. That's a +2 overall there. I should get my calculator out in a second here. So in this particular case, if we sort of put together everything we got going on, we have a -12 that's left over. Different as well here, our chromium, we don't have one, but we actually have two of them. So for each of those, again, to get us to -12, the chromium here has to be actually +6 each, right? +6 here, +6 here gets us a +12, which again would balance out the charge. So again, we don't want to give the total adding up there. Potassium +1, chromium only +6, not +12, and oxygen here -2, not -14. Any questions on how to assign oxidation numbers? And again, being able to sort of correctly assign oxidation numbers will definitely help you when you're doing your sort of redox reactions and balancing those redox equations or writing the half reactions, which is again some of the study assignment and the lab that's coming up this week and the next is being able to do these things correctly. Any questions on that? They hopefully should agree with us. Now, as I mentioned before, like the double displacement that came before it, the redox reaction, again, is sort of a big umbrella under which we could classify different types of reactions. The first type that we could put under there is a combination or synthesis reaction. And in a combination or synthesis reaction, the general formula is A plus B makes A and B. You're essentially putting things together. So two things make one, combination or synthesis reaction, as we can see there. So this is aluminum plus bromine gives us aluminum bromide, which is again, two things make one thing. This could be classified as a combination or synthesis reaction, but it also could be classified as a redox reaction. The aluminum here, which is by itself, has an oxidation state of 0. The aluminum, when it gets with the bromine, has an oxidation state of +3. The bromine here has an oxidation state of 0. The Br is -1 here. So when we look at the aluminum, it is going from 0 to +3, which means the aluminum is going through oxidation. And when we look at the bromine, it's starting at 0 and going to -1, which means it's going through reduction in this case. And it is still a redox reaction as well. By the way, in this case, since the aluminum is going through oxidation, this would be our reducing agent. And the bromine, which is going through reduction, this would be our oxidizing agent in this case. Now, another type of redox reaction is a decomposition reaction. And in a decomposition reaction is basically the opposite of a synthesis reaction. You start with one thing and you break it apart into 2 or more things. So if we look at this here where we have potassium chlorate and we break it apart into potassium chloride and oxygen gas, again, this could be classified as a decomposition reaction. It is also still a redox reaction that is occurring here. Again, if we assign some oxidation states, the oxygen here is -2. That gives us -6. The potassium is +1 in this case. So again, to balance it out here, our chlorine is +5. Coming on the other side, our potassium is +1. Our chloride is -1. And our oxygen is 0. When we look at what's happening, the potassium is not changing, but the chlorine here is going from +5 to -1. So +5 would be over here, and it's heading towards -1. So what we see with the chlorine is it is going through reduction, going from +5 to -1. Oxygen, on the other hand, is starting at -2 and heading towards 0, which means the oxygen here is going through oxidation. Is it right out of room over there? So again, although this could be classified as a decomposition reaction, which it probably will be classified in most cases, overall, what's truly happening here is still a redox reaction. Any question on those two? So again, under the big umbrella, we have synthesis or combination and decomposition, which are types of redox reactions. Now, a combustion reaction is also a redox reaction. And here, if we look at sort of what's happening in terms of the oxidation states, we have sulfur, which is going from 0 to +4 in this case. And again, going on our number line from 0 to +4 means it's going through oxidation. While our oxygen is going from 0 to -2, which means it's going through reduction in this case. And it is a redox reaction. So this is an example of a combustion reaction. This is also an example of a combustion reaction. The basic definition of something that's considered a combustion reaction is that there is O2 present. So here we see O2 present. Here we see O2 present, and it is a combustion reaction technically. Also a redox reaction, as this is 0, 0, as we saw earlier, +2 and -2, where magnesium is going through oxidation, the oxygen is going through reduction. And in addition, both of these reactions are technically a synthesis reaction as well. 2 things make 1, 2 things make 1. So these couple of reactions here, you can actually classify in like 3 different ways: combustion, synthesis, or even a redox reaction. Now, this type of combustion reaction, which is sort of a generic definition of combustion, which basically means you just need oxygen present, is not to be confused with another type of combustion reaction, which is an organic combustion reaction. And in an organic combustion reaction, we start with an organic guy, which is basically like carbon, hydrogen, or oxygen. We add oxygen to it, and we get CO2 and water. So if you have more of a classic organic combustion reaction, which is a lot of times what people think about when we think about a combustion reaction, that's essentially the reaction where you will definitely get these 3 things. So for example, if you took methane, which is the simplest organic molecule you got, like when you light a Bunsen burner, you get CO2 and water here, and like maybe a 2 there to balance, and maybe a 2 there as well. And this is your classic organic combustion reaction: O2 on the reactant side, CO2 and water on the product side. Now, this reaction that we saw before is also a redox reaction. And you could also get very specific about these type of reactions. Most people will classify this reaction, as I mentioned earlier, as a single replacement reaction, where again, the generic formula is A plus BC. And again, this is an ionic compound. This guy, if that's a metal coming in and kicking it out, gets you A and C, and B coming out by itself. So this is usually what is classified as a single replacement reaction, but you can also get very specific in terms of what's happening. In this case, the strontium is coming out and kicking the hydrogen, and this is sometimes what is referred to as a hydrogen displacement reaction, because when we kick out hydrogen and it becomes by itself, we get hydrogen gas, which is the bubbles that you typically will see. This next one is what is referred to as a metal displacement. So again, the magnesium with no charge will come and kick out the metal that has a positive charge. And this is what is sometimes referred to as a metal displacement reaction, because the metal is replacing the metal. And it's still the same thing in terms of a single replacement reaction. And lastly, our halogen, like in that experiment we were talking about earlier, when the halogen comes in with no charge, it will kick out the negative guy. And what we get is, again, a halogen that has been displaced, which is a halogen displacement. All 3 of these represent single replacement reactions. The hydrogen displacement, the metal displacement, or the halogen displacement are a more specific way to classify a single replacement reaction. And as you can see with the oxidation numbers written above, they are all as well redox reactions as well. So they all fall under that redox sort of category. In the first one, the strontium is going from 0 to +2, being oxidized. The hydrogen is going from +1 to 0, being reduced. The magnesium is being oxidized in the second one. The Ti is being reduced. The chlorine is going through reduction, while the bromine is going through oxidation in the last one. Again, just to show you that, we have our chlorine that started at 0 and ended at -1, which means it's going through reduction. And our bromine started at -1 and went towards 0, which is going through oxidation. So again, you can kind of use that little number line to help you out, figure it out. Also means in this case, this which is going through oxidation, this would be my reducing agent. And our hydrogen here, which is going through reduction, will be my oxidizing agent. This going through oxidation will be my reducing agent. This would be my oxidizing agent, which is going through reduction. And here, The Cl, which is, again, going through reduction, would be my oxidizing agent. The Br minus here would be my reducing agent in that case. So the overall guy, a single replacement, you could get specific about the type of single replacement reaction that's happening, where you could classify as a hydrogen, metal, or halogen displacement. And again, they're all under the big umbrella of redox reactions. And just like we talked about before, in order for this to happen, whatever is coming in needs to be more reactive than what it's replacing. And again, if it is not, then this reaction will not take place. So let's take a look at what can help us decide that. This is what is sometimes referred to as an activity series, sometimes as an activity series of metals, which is a little bit not as in depth as this one. And in a basic sort of activity series, much like here, there's a whole bunch of metals, hydrogen somewhere in the middle. There's other metals sort of listed, sort of like what we got going on this side of it. And typically on these lists, whatever is higher on the list is more reactive than what's lower on the list. So that means anybody higher on the list will replace somebody in a single replacement reaction by somebody lower on the list, and vice versa. If somebody's lower on the list, it will not replace anybody higher on the list. So when we look at calcium and water, calcium is up here, and calcium would be coming in to replace hydrogen. And again, it's higher on the list than hydrogen, which is down here. So this reaction will take place. Now, if we took the lead and wanted it to come in to replace the hydrogen, what we would see is when we look at it, although they are close here on the list, in order for lead to actually replace and produce hydrogen gas, it would have to react with an actual acid, which water is not an acid in this case. So because it cannot act with the water, this reaction will not take place. So this one's a little bit more in detailed sort of a list than a more generic activity series like I described up here. This one gets very specific about, do you need water to do it? Do you need something stronger like an acid to make this reaction sort of take place? And again, you could kind of use that. If you needed an activity series, it would be provided for you in the basic sort of way, where again, it's just a bunch of elements, hydrogen in the middle. And again, anybody higher on the list is more reactive. And anybody lower on the list is less reactive towards the bottom. Now, our halogens, if you remember from that experiment that we've been talking about, we actually figured out the activity series of the halogens. And if you remember from that experiment in group 7, reactivity increases as you go up group 7. So when we look at this one, when we compare the chlorine coming in to kick out the bromine, when we look at group 7, we have the fluorine, we have the chlorine, we have the bromine, we have the iodine. Because chlorine is higher in group 7 than bromine, as we saw in that experiment, chlorine is more reactive than bromine. So this reaction will take place. Now, if we try to do it with the iodine here to replace the bromine is higher on the list than the iodine. And that means the iodine is actually less reactive. So because it's less reactive, this reaction will not take place, and you will get a no reaction that will actually take place. So the activity series for our halogens is pretty much group 7, like that experiment we did. Gosh, I think it was maybe experiment 3, where we saw that the activity increases as you go up group 7. Any questions on that there? Now, one last thing in terms of oxidation and reduction reactions is you could actually have the same element doing both. So you can have the same element that is going through both oxidation and reduction in the same reaction. When we look over here, our chlorine is 0. And when we look over here, our oxygen is -2, our hydrogen is +1. When we come over here, our oxygen is -2. Now the chlorine here, it does have an overall charge of -1, this whole thing. So that means that the chlorine in this case would be +1, while the chlorine in this case would be -1, hydrogen here +1 and -2. So again, in terms of the oxygen and the hydrogen here, not much happening on either side. But when we look at the chlorine, in one case, this chlorine is going from 0 to +1 on the other side in terms of its oxidation state, while our same chlorine is going from chlorine to a chlorine with a -1 in terms of its oxidation state. In the first case, is going from 0 to +1, which means it's being oxidized. While in the second case, it is going from 0 to -1, which means it's being reduced. So very common in atmospheric chemistry, you will see that occur where chlorine gets both oxidized and reduced at the same time. And basically you would write the two half reactions based on, each of them separately. So basically this would be the half reaction. You would actually include that in this case. And the other guy would be the Cl- on this side here. So this is what's referred to as a disproportionation reaction, where one element gets both oxidized and reduced at the same time. So these are just some different ways that we could classify reactions. Again, there's multiple ways that you could kind of classify it. This is a net ionic equation. The first one where calcium carbonate would make a precipitate. So this would be a precipitation reaction, which again is under the big umbrella of double displacement reactions. This is your net ionic equation. The second one for reaction of an acid and a base, which is an acid-base reaction, also under the big umbrella of double displacement reactions. The third one there is our redox reaction, which is sort of the big umbrella. This again is a hydrogen displacement where the zinc would come in and kick out the hydrogen. So you could call it a hydrogen displacement. Most people will probably call it a single replacement. Are it again under the big umbrella of redox. And lastly here, this is a synthesis reaction. A lot of people would call it. It is also again a redox reaction, as that's 0, 0, that's +2 and -1. By the way, this is also a redox. There's 0, +1, -1, +2, -1, and 0 in terms of our oxidation states. So what you can see here is there's many different ways you could even classify a single reaction, depending on sort of what aspect you're looking at. Again, sort of the two big umbrellas is our redox reaction and double displacement, which underneath each of them are different ways to classify. Any questions on that? Okay, so that will wrap it up for this chapter. So before we officially finish here for lecture, let's just talk about a few things. We'll be moving on to the next chapters, which should be up there, kind of a combination with some different things, but essentially it's going to be stoichiometry, limiting reagents, percent yield, and solution stoichiometry. and also molarity and stuff like that. So that's what's coming up. At this point, again, like I put up earlier, you have study assignment E, I believe, which is net ionic equations. That is due, I think, towards the end of this week. That is something you should already be able to have done or be able to work on, obviously, at this point. You also have study assignment F, which is redox reactions, balancing redox reactions and stuff like that, oxidation states. And experiment number 9, which is basically the oxidation reduction of iron. Now, for experiment 9 and study assignment F, you could probably work on most of that. But there is some stuff that we're just going to talk about during lab, and we're going to do that today. So during lab, we're going to open up a lab lecture. We'll take a little break in between this one and that one, and I'm going to talk about how to balance redox reactions like the ones that you'll find both in experiment 9 and also study assignment F. So I believe in experiment 9, you have some post-lab questions that will require you to balance redox reactions correctly. And study assignment F is all about that. So we usually cover this in a day in lab. So we're going to do that today. So after this, we'll take a break. I'm going to open up the lab lecture, and I'm just going to lecture a little bit. We're going to do some examples, and that should then allow you to have enough information to complete experiment 9 and also study assignment F. So I believe study assignment F and experiment 9 are due next week. And I believe study assignment E, which is the stuff we sort of finished last time, and I said you should get started on that, should be due this week, at the end of this week. Any questions on any of that there? So again, there will be a very short lecture on how to properly balance redox reactions like you'll find in those study assignments and the experiment. And we'll do that after we take a little break here and start lab. Any questions on any of that stuff? In terms of the scheduling, again, we're going to get into molarity and solution stoichiometry. So titration will be pushed back until probably sometime next week. We'll officially sort of start the titration experiment and all that. So we'll be working on these 3 sort of things through this week and into next week. And hopefully by next week, we'll hit enough information to maybe start some of the titration stuff. Any questions on anything? Okay, so we went a little bit long here, but why don't we take maybe a 15-minute? Well, we'll start about 7:20. How's that? So about 7:20, I'll open up the lab one, so you have to relog back in if you want to listen to it. Obviously, afterwards, I'll post both of these up once they get done processing and all that good stuff on Canvas. So let's make a 20-minute break, and we'll start the lab, and we're going to cover again how to balance redox reactions in acidic and basic conditions, and we'll do some examples. All right, if there's no other questions, still working on your exam. I'll do my best to try to get those graded shortly, and at some point after I grade the exam, I will obviously upload an updated grade of where you're at this moment, okay? All right, I'll see everybody in about 20 minutes in lab.